Hey everyone. So in this video, I like to say a few more things about function transformations. In particular, I like to talk about stretches and compressions. So we've already talked about a few transformations so far, horizontal shifts, vertical shifts, and reflections. And so I like to summarize those ideas in this table below. So if I have some function f of x, and I add some constant to the end of it, directly to the function itself, well, what does this do to the graph of our function? The resulting graph of f of x plus c, well, it looks like f of x, but it's shifted up c units if that constant that we're adding on is positive, and it's shifted down if that constant that we're adding on is negative. And then if we add to the input of our function, if I have f of x plus c here, where that plus c is contributed into the input of this function, sort of surprisingly, this graph shifts left if c is it should be greater than 0. Right, if we have some positive number that we're adding onto this input, that shifts our graph left c units, and if c is less than 0, that shifts our graph right. Now for reflections, if we go ahead and negate our output of our function, the function itself, this amounts to a reflection over the x-axis. This is a vertical reflection. Right, so if I have this x-axis here, really what we're doing is we're sort of flipping our graph over this line. And then if we have f of negative x, we negate the input of our function, well, that reflects over the y-axis. Right, so this is a horizontal reflection. And so, a few things to point out is that when we do something to the output of our function or to the function itself, then that amounts to some sort of vertical transformation. And if we apply some sort of transformation to our input, then that amounts to a horizontal transformation. Okay, and so here we've yet to talk about stretches and compressions, and that's really what I'd like to focus on in this video today. And so when I say stretches and compressions, maybe I'll just include them in this list. Really this amounts to multiplying by some constant to either our input or our output. And kind of in the same vein as all of our other transformations so far, if I take some constant and I multiply to the output of my function, this is going to amount to a vertical stretch or compression. If I take some constant and multiply to the input of my function, well, it's going to amount to some sort of horizontal stretch or compression. And so I want to explore this in a little bit more detail. So let's start with this function f of x is equal to the square root of x. So we've graphed this function a handful of times now, but really again to help us out in understanding how this transformation works, I would really like to make a table of this function. So here we have x and f of x, and some nice numbers we can plug into this function are 0, 1, 4, 9, and 16. And what we get out are 0, 1, 2, 3, and 4. And so the transformation I'd like to look at is the one where we take 3 times our function, f of x. In other words, this is really the same thing as 3 times the square root of x. Right, so what does this function look like? Here, if I make a table for 3 times the square root of x, well, if I take my same input values, 1, 0, 1, 4, 9, and 16, what happens, well, I take 3 times the square root of 0, and I still get 3 times 0, that's 0. If I take 3 times the square root of 1, I get 3 times 1, that's 3. If I take 3 times the square root of 4, that's 3 times 2, and so that's 6. 3 times the square root of 9 gives me 3 times 3, or 9, and then 3 times the square root of 16 is 3 times 4, that's 12. And so if this is my function, the graph of my function, the square root of x, So here's f of x is equal to the square root of x. Then what's happening with our 3 times our square root of x function? Well, we see the points 0, 0, 1 with an output of 3, 4 with an output of 6, so it's already past the edge of my grid. And so here I can sort of see that this graph would look something like this. And so it looks significantly larger. The graph goes way higher than our original f of x is equal to the square root of x graph. And so here this is 3 times f of x. And really the takeaway I want you to have here is that all of the points that we see here from our original function are stretched upwards by a factor of 3, right? Their output was multiplied by 3, and so now they're 3 times higher. And so again, this isn't a shift or anything. This is a stretch, right? Here I can notice that it got multiplied, stretched out by a factor of 3, and so it went up to an output of 3. But here, it didn't get shifted up a handful of units. It got stretched by 3, and so this output of 2 went to an output of 6. Right, so it doesn't quite act evenly on all of the points. They're all being stretched away from the horizontal axis, right? But really what we're having here is a vertical stretch by a factor of 3. So multiplying our function by 3 took all of the outputs and multiplied them by 3. In other words, we vertically stretched our graph by a factor of 3 away from our horizontal axis. All the points were stretched away from the horizontal axis by a factor of 3. Now let's take a look at what happens if we multiply by some small number, right? So if I have f of x is again equal to the square root of x, and let's say we look at 1/2 times f of x, in other words 1/2 times the square root of x. Well, what does the table for this function look like? Well, if I again plug in the same inputs 0, 1, 4, 9, and 16, well, really, I'd take 1/2 of the same values that we saw before, right? 1/2 times the square root of 0 is equal to 0. 1/2 times the square root of 1 is 1/2. 1/2 times the square root of 4 is 1. 1/2 times the square root of 9 is, well, the square root of 9 is 3, and so 1/2 of that is 3/2, and then 1/2 times the square root of 16, that gives me 2. And so I'm not going to be able to plot all these points on our small grid, but here if I look at the graph of our square root of x function, then the points we can see here on our 1/2 f of x, well, I still have that point 0, 0. When I plug in 1, I get 1/2. When I plug in 4, I get 1. Really, the values we see here are half as large as the values of our original function. Right, so here, what happened was that the graph was compressed down towards our horizontal axis by a factor of 1/2. Right, all of the y values, all of the output values got multiplied by 1/2, and so they're scaled down closer to the x-axis. All of their output values were cut in half. And so in general, so the transformation where we take some constant and we multiply it to the outputs of our function, well, this really corresponds to a vertical stretch or compression of our f of x function, of our original function. And we saw that, well, if we take some large number and we multiply it to our function, if we take some number larger than 1, then our outputs are going to scale upwards away from the x-axis, away from the horizontal axis. So if c is greater than 1, the graph will stretch. And it'll stretch away from the x-axis. Right, vertically away from that horizontal axis. And if our value of c is some small quantity, like some fraction value less than 1, so here I'm just considering positive values. So here c is less than 1, then the graph will compress. Here it'll get scrunched towards the x-axis, or the horizontal axis. So let's go ahead and apply our new ideas to this graph here. So let's call this graph f of x. I want to sketch the graph of our transformation 2 times f of x. And I definitely encourage you to pause the video and try this example out yourself. See if you can identify a few points on this graph of the new function 2 times f of x. So 2 times f of x, what does this do? We're saying that multiplying 2 to the outputs of this function is going to stretch all of the outputs by a factor of 2 away from the x-axis, away from the horizontal axis. So here, this point of 6, 2, its output is going to get stretched by a factor of 2, and it's going to get moved to this point here, 6, 4. And similarly, this point down here at -4, or +4, -2, it's going to get stretched by a factor of 2 away from the x-axis. And again, this isn't shifting, it's going to be stretching away from our x-axis, and so it's going to get pulled out away to this point here. It's going to have its y value multiplied by 2, and it's going to result in the y value of -4. Right? But the x value doesn't change. This point here, it's going to get stretched by a factor of 2 in the vertical direction, and so its y value is going to come out to be 2. After this transformation, this point here is going to get stretched away, and it's going to have a y value of -4. This one here is going to come out with a y value of -6. And then this one here, that looks like it's at a y value of 1 or 3.5. It's hard to say, but it looks about right. Would come out to a y value of -7. And so we can sketch the graph, the curve, really, connecting all these points, recognizing the shift of this, or not the shift, the stretch of this original function. And we know how the shape of this function is going to look. It's going to look something like this. So maybe I can do that one a little bit better. Right, so here, the points above the x-axis are going to get stretched upwards. The points below the x-axis are going to get stretched downwards. And the point on the x-axis aren't going to move at all. Right? If that vertical stretch is stretching away from our x-axis, then the points on the x-axis are going to stay there. And so that's a rough sketch of our stretched out function, 2 times f of x. Okay, so let's go ahead and try to do the reverse. So here I have a graph and I want to find an equation for this function. One thing I notice is that it looks parabolic. It's going to be some transformation of our function f of x is equal to x squared. And so before we really dig into things, let me encourage you to pause the video and again try this example out yourself. See if you can come up with the transformations necessary and how they would look in the corresponding equation of this graph. Right, so here we're saying that the parent function, sort of the base function that we can imagine starting with, is the function f of x is equal to x squared. And this is some transformation of the x squared function. It's a parabola. And there's a few things going on. One thing I notice is that there is a vertical reflection. Right, so here there's a vertical reflection. Because our parabola is opening downwards. Another thing I see is that this function is shifted to the right 3 units and shifted down 1 unit from our typical f of x is equal to x squared graph. And there's also some stretching going on. If you're pretty familiar with the x squared function, you might be able to identify this just by looking at it. But if not, that's okay. We can do some mathematics to figure out exactly what the stretch is. So there's some sort of stretch. And so here, if I call this function g of x, then what g of x looks like is, well, there's going to be a vertical reflection that amounts to negating the output of my function. And there's also going to be a vertical stretch, right? So actually, I should include some constant here, a. That we can figure that out in a moment. But this is going to be a times f of. Now, how do I convey a horizontal shift of 3 units to the right? Well, this comes from subtracting 3 from the input of our function, right? Having the input x take away 3 is going to shift our function 3 units to the right. And then the last thing is I want to shift 1 unit down. So that's going to be a -1 at the very, very end of my function. And so here we've really got most of this new function here. This g of x is negative a times, well, f of x minus 3. What is that? That's f is a square function. This is x minus 3 squared. Take away 1. And really we just have to figure out this vertical stretch we've got going on here. And we can do some algebra to figure this out, right? I know that this point, I mean, there are many different points we can use, but this is one example of a point that belongs on the graph of my function. In other words, it should make my function true. If I plug in 4 for my input, I should expect -3 as my output. And so we can use this to figure out the value of a. Right? So if I plug in 4 for the input of this function, I expect to get -3 for the output of this function. And so here, that tells us that we have the equation -3 ought to equal -a times 4 minus 3 squared, take away 1. And now this is just an equation in one variable now. And so we can solve this equation and figure out the value of a. So I can add 1 to both sides to get -2 is equal to -a times 4 take away 3 squared. I can also sort of simplify this bit. Right, 4 take away 3, that's just 1. Right? So this is -2 is equal to -a times 1 squared. And 1 squared isn't really going to, it's just 1 again, and multiplying that to a is just going to be, well, it's going to leave it alone. So I have -2 is equal to -a, and so that tells me that a is equal to 2. This function, it's stretched. It's a stretch of our parabola by a factor of 2. And then it also includes a reflection over the x-axis, a vertical reflection. And so at the end of the day, this function g of x can be read off as -2 times x minus 3 squared, take away 1. So we've made sense of vertical stretches and compressions. Now let's take a look at horizontal stretches and compressions. And let's use this function f of x is equal to x squared. So if f of x is equal to x squared, what is f of 1/2 x going to look like when I scale the input of this function by some small number here? So maybe to make things a little bit more explicit, this is like inputting 1/2 x into my f function. That's the same as taking 1/2 x and then squaring it, right? Replacing the input of our square function by 1/2 x. So here, let's make a table to really unpack what's going on here. So here's x, here's f of x, and we're pretty familiar at this point with the inputs and outputs, at least some nice values for this function f of x, right? It just squares my input. Now what about for this new function? Well, if I plug in 0 into this new function, what we're really doing is we're going to take 1/2 of 0 and then square it. So we're going to square 0 here, and we get 0 out. Now what if I plug in 1 into this new function? I get 1/2 times 1 squared is equal to, well, that's going to be 1/2. I'm going to square that. That's going to give me 1/4. So not a very nice number. But if I plug in 2, I get 1/2 times 2 squared. That's going to be, well, 1/2 times 2 is 1, and then I'm going to square that, and I get 1. So we got a nice value there when we plugged in 2. What's another number we could plug in to get a nice value? Well, I can imagine plugging in 4. That'll give me 1/2 times 4. I'm going to square that result. That's going to give me 2 squared. And I can also plug in 6. Right, 1/2 times 6 is going to give me 3, and then I'm going to square that to get 9. And really, the numbers I want to plug in to get my nice results or nice values that I'm familiar with my squared function, the numbers I really want to plug in are twice the value of the original inputs that we were plugging in for f of x is equal to x squared. Right? So really, to obtain the same outputs, as our f function, we should plug in values or input values twice as large. Right? Because of this factor of 1/2 here, really for me to come out with the same outputs, I need to plug in twice as large inputs. Right here we saw that to plug in 2 into my function gave me that output of 1. To plug in 4 into my function amounted to squaring 2. Plugging in 6 into my function amounted to squaring 3. The values we're pretty familiar with our x squared function. I need to plug in twice as large values to obtain my same outputs. In other words, I really need to look further out along my x-axis to obtain my same outputs. And so here, let me sketch the graph of this function. And I guess I should say that symmetrically, if I plug in -2, -4, and -6, those are going to give me the outputs 1, 4, and 9 respectively. Right, so here's my f of x function. And so we have to plug in twice as large inputs to obtain the same output. So really to obtain an output of 1, I needed to plug in an input of 2. Oops, sorry. Should be this point out here. Really to square 2 in this function, this new function, I really had to plug in twice as large of an output. I needed to plug in 4 to get 4 out. And similarly, if I plug in negative values, if I plug in -2, that amounts to squaring 1, -1. And if I plug in -4, that amounts to squaring -2. And so really, my graph is stretched out horizontally by a factor of 2. This 1/2 told me I needed to plug in larger outputs. I needed to look further along my x-axis, away from the origin, to obtain the same values as my original function. This f of 1/2 x, it really stretched my function horizontally by a factor of 2. Okay, so let's go ahead and scale the input of our function, but instead of scaling it by some number, some small number, let's go ahead and scale it by a factor of 2. So let's multiply our input by 2. And so this amounts to taking, well, 2x and then squaring it. If we're talking about f being that same x squared function. Okay, so this is my f of x function. F of x is equal to x squared. So let's go ahead and make another table for this function here. So here this is x, this is f of 2x, right, which is the same as 2x as a group squared. If I plug in 0, this is the same as 2 times 0, and then squaring that, it's going to be 0. If I plug in 1, this is the same as, here maybe I'll move this down. If I plug in 1, this is the same as taking 2 times 1 and then squaring that, so I get 2 squared, which is 4. If I plug in 2, I get 2 times 2 squared, this is 4 squared, this is 16. These values are getting large real fast actually. And so here maybe let me plug in a smaller value like 1/2. If I plug in 1/2, I get 2 times 1/2 squared is 1 squared, or in other words 1. And so that would tell me also that negative 1/2, when I input that, I get 1. If I plug in 1, or if I plug in negative 1, I get 4, and if I plug in negative 2, I get 16. Well, if I were to plot these points out, I see this 0, 0, 1/2, comma 1, 1, comma 4, negative 1/2, comma 1, negative 1, comma 4. Here, to get the same outputs as our original f function, right, to get these same outputs to square 1, to square 2, to square 4, I had to plug in a half as large of a value. Right, because of this factor of 2, I needed to plug in half as large of a value, an input value, to get the same squares that we're familiar with. Right? So plugging in 1/2 amounted to squaring 1. Plugging in 1 amounted to squaring 2. Plugging 2 amounted to squaring 4. And so really, going half as far along my x-axis is going to give me the same values of our function, our f of x function. And so really what this 2 times our input did was that it really cut our input values in half. It compressed the inputs by a factor of 2. Right? All of the points are the same, but their x values are squeezed in by 1/2. Right? They're closer to the y-axis. And so in general, the transformation f of some constant times the input of our function, this horizontally stretches or compresses our function f of x. And so, like many of the ideas behind this input, or influencing the input, transforming the input, sort of works backwards to what you expect. We get a stretch when we have small values of c, when c is less than 1. Or when we had a factor of 1/2, it stretched out our function, the graph of our function, by a factor of 2. And when we get compression, that occurs when we have some larger input. We're sort of running through our inputs faster. Like for example, here, this 2 times x is saying we're going through our inputs twice as fast. And so all of those outputs are going to happen earlier along our x-axis. And so here, let's update this in our table. Right, so here, now that we've really discussed stretching and compression, or now that we've really discussed stretching and compressing functions, we can write those ideas down here. So here, if c is greater than 1, we get a vertical stretch. When c is less than 1, we get a vertical compression. When we multiply to the function itself, we get a horizontal stretch when c is less than 1, and a horizontal compression when c is greater than 1. Okay, so let's apply this idea. Here I have some function f of x, and I want to determine or graph the transformation f of 1/2 x. And so please pause the video, try this example out first, and then we can talk about it together. So this f of 1/2 x, this scaling of our input by a factor of 1/2, this is going to stretch our graph horizontally by a factor of 2. And so all the points we see on our graph, they're going to get pulled out by a factor of 2 away from our y-axis. So here, this point of 6, 2, it's going to move all the way out. It's going to get stretched all the way out to this point 12, 2. And this point 4, negative 2, that's going to get stretched out all the way to this point 8, 2. And then this point's going to come out to 2, 1. This point here is going to come out to negative 4, negative 2, and this point here is going to come out to, what is this? This is negative 10, negative 3.5. And so the graph of this function, it looks something like this. I feel like this part's going to be hard. I can do it. Let's do it here.